right, the last thing we want to talk about before we end the year is this idea of a three-dimensional solution. Now, there's a lot of things that we didn't talk about this year, such as three-dimensional graphing, that may have been helpful for us to be able to actually get a better idea of what's happening here. But we're just looking at a quick overview of what it means to have a 3x3 system and how to solve it. Next year, you're going to learn some interesting ways to solve these systems of equations. But for this year, you want to take a look at, how we can use some of the strategies that we already know. So to kind of take a look at that, if we go back to something that we've seen before with a 2x2 system, our goal is to figure out what the solution to this system of equations is. Now, in Algebra 1, you looked at a few different ways to solve these types of equations. You looked at graphing, and by graphing, you looked for what type of solution there was. If you had parallel lines, that meant there was going to be no solution. If you had intersecting lines in some way, that meant there was one solution. And if you ended up graphing the same line twice, you ended up with an infinite number of solutions. And we're going to see those same types of things happen even within solving with algebra. So with algebra, to get no solution, you end up with something, in the end that looks like, maybe 0 equals -3, something that makes no sense at all. You could end up with something something like 4 equals 4. That tells you that there's going to be an infinite number of solutions. Or you could get something like x equals 3, which will tell you that there's going to be one solution. Now, with a 2x2 system, we had 3 ways we could solve. We could graph, or algebraically, we could use substitution, or we could use elimination. I'm going to stick with elimination because when we get to these bigger systems, elimination is going to be a necessary thing for us to use. So elimination basically just says, can you take this equation or this system of equations and take it from 2 equations with 2 variables and get it to a place where it's just one equation with 1 variable, because then that's something we can easily solve. So to do so, we look for one of 2 things happening. Either one of our variables in both equations has the same coefficient like we see here. One would be negative, one would be positive. Or we might see an opportunity to create that variable with the same coefficient. But once we get it to a place where they have the same coefficient, then we usually try to make it so that one of them, again, is negative and one of them is positive. We can just add the 2 equations together. Because what happens is we get 42x, but then these end up just adding to be 0. Equals, so that's going to be 84. And now we have an equation with 1 variable that we can easily solve for x. And then what we can do is we can go back to the beginning and plug in our solution into one of our other equations. So let's say 12 times x, 12 times 2, minus 2y equals 16. And we get a way to then solve for y. And I'm not going real slowly here because I think this is something that we know how to do. But the important thing to remember is that our solutions are always written as an ordered pair in xy form. So that would be the 0.24. So that is what we already know how to do. Now, if you're really curious about what this looks like graphically, you could go ahead and use this link and graph these 3 equations. And what you're going to see is that each of these with 3 variables, and let's think about this. When we graph an equation with 2 variables, we get a line. When we graph an equation with 1 variable, we get a point on just a number line. But when we graph an equation with 2 variables, we get a line on our xy plane. If we graph an equation with 3 variables, what you're going to end up with is a plane on a 3-dimensional coordinate plane. So we're not getting any further into it than that. If you're curious about what this looks like, go ahead and go to those links and type in those equations, and you can kind of play around with it and see. It's a kind of a neat thing. But we're not going to do that. What I want to do is I want to talk you through how we actually work through solving a system of 3 equations and 3 variables. And the first thing I always do is I number my equations because it's going to make it easier to stay organized. So again, what I look for, and what, like I said before, we want with a three-dimensional system or a larger system of equations to use elimination. Our goal right now is to take this, which is a system of three equations and three variables, and find a way to whittle it down so that it's an equation, a system of equations with two equations and two variables. And the way we're going to do that is by eliminating a variable completely. Now, the goal is we have to come up with two equations that only have the same two variables in them. So I look at my system and I see some things happening. I see that there's a 2x and there's a 2x. So that would make an easy elimination like we did up above. I could, multiply everything by -1 here, add the two equations together. But that's only one time that I've gotten rid of x. I'd still have to eliminate x again. Well, I see that 2 and 6 are closely related. So theoretically, I could take this equation and multiply it by 3 or -3 and then add it to the second equation. Or I notice that all three of my y's have either a positive or a -3 with them. So here's what I'm going to do. I'm going to take the first equation, so equation 1, which is 2x plus 3y plus 3z equals 6, and I'm going to add that to the second equation, which is 6x minus 3y plus 4z equals 12. Now, when I add those two equations together, something really nice is going to happen. I'm going to completely eliminate my y. And what I'm left with is 8x plus 7z equals 18. Now, I'm going to call that equation 4. Okay, that's a brand new equation. I'm going to call that equation 4. So now I have one equation with two variables. What I need to do next is take two equations, again, going back to my original 3. Now, I can't use the same 2 I already used, or I'm just going to end up with the same equation again. I need to use two different equations. So this time, I'm going to pair up equation 1 plus 3y plus 3z with equation 3. Now, I hope that you can see why I did that, and I'll tell you why. Because I can add these together, and once again, my y's will end up being 0. So that's going to give me 4x, no y, plus 5z equals 12. Now I'm going to call that equation 5. So now when I look at equations 4 and 5, I'm just going to write them over here for a second. Really nice thing, right? I've got two equations with the same two variables with x and z. This is just like what we did up here. Okay, we had two equations with two variables. We just have to use the strategies that we've been using since Algebra 1. Again, I like elimination mostly because most of the time I can avoid using fractions like I would if I were going to do a substitution. The key here is, though, I don't have the same coefficient in front of any of my variables, right? I've got 7 and 5 in front of z, and I've got 8 and 4 in front of 2. But what's nice is if I multiply 4 by -2, I'm going to get -8, and then I can add those together. So that's what I'm going to do. I'm going to say, let's multiply, the second equation by -2. Now, don't forget to multiply everything in that equation by -2. So that takes my equation 4, 8x plus 7z equals 18. And it's going to give me this equation 5 written after I've multiplied everything by -2. So I'm going to have -8x minus 10z equals -24. And then I can go ahead and add those two equations together. Again, that's going to eliminate a variable for me, right? So now I have -3z equals -6. Now, I just found z. Z is 2. Awesome. From that, I'm going to need to go ahead and use my other equations to find the other two variables. So maybe I plug in z equals 2 into equation 5. Okay, so I'd have 4x plus 5 times 2 equals 12. And that gives me, 4x? So I'd subtract 10 from both sides. and I would get 4x equals 2, x equals a half. And then I can go ahead and plug in 1/2 and z equals 2 into one of my original equations. So let's do the first equation. So let's just plug this into equation 1. So 2 times a half plus 3y plus 3 times 2 equals 6. And then from there, I can continue to solve this. So I would have 1 plus 3y plus 6 equals 6. That's going to give me 3y equals -1, so y equals -1/3. So I've got all three variables. I figured out a value for all three. So I can write my solution instead of as an ordered pair, as an ordered triple. So that's going to end up being 1/2, -1/3, and 2 for our solution. All right, so we're going to try a couple of these sort of together, and I'm going to walk you through the process here. So when I look at the three equations with three variables, I've got to figure out which variable I want to eliminate. And so I try to decide which one's going to be the easiest. So in front of x, I have a 1 and a 1 and a 2. That's promising. In front of y, I have -3, -1, and 2. Three completely different three completely different coefficients. That might be a little more challenging. And z is the same as y. So I think what I'm going to do is I'm going to stick with trying to eliminate x as a variable. Now, to do so, I'm going to have to multiply each equation, theoretically, by something. So I'm going to take number 1, and I'm going to multiply number 1. So let me write this out here. Here's step 1. I'm going to take number 1, x minus 3y plus z equals 1, and I'm going to pair it up with number 3. Okay, so now to do this, you really don't have to multiply by anything, right? We could just subtract these two equations. Or if it makes you happy, go ahead and multiply equation 3 by -1 and then add them. Either way, if you subtract them, we're going to get 0x, -3y minus 2y is -5y, z minus -3z is plus 4z equals 1 minus -1, which will be 2. So I'm going to call that equation 4. Now I'm going to pair up equation 1, which is x minus 3y plus z equals 1. And I'm going to pair that up with equation 2. But the trick here is I'm going to have to multiply equation 2 by something equation 1 by something first, so that I can actually add the two equations together and eliminate x. Remember, that's my goal. I need to eliminate x again so I can end up with a second equation that only has two variables in it. So the best guess here is let's go ahead and multiply that first equation by -2. All right, so then that gives us equation 1 as -2x plus 6y minus 2z equals -2. And then equation 2 as 2x minus y minus 2z equals +2. And then we can go ahead and add those equations together. All right, and when we do so, we get 0, right? And then we get 5y minus 4z equals 0. Okay, so let's call that equation 5. Well, then let's go ahead and add or look at equation 4 and 5 together. -5y plus 4z equals 2. And equation 5, which is 5y minus 4z equals 0. Now, the great thing is we've only got two variables there, and they're the same two variables, which is also really helpful. I noticed right away that I've got the same coefficient, one positive, one negative, in front of y. So let's go ahead and add the two equations together. Something interesting happens here, because those both add up to 0, and those both add up to 0. So we get 0 equals 2. So what we found with two equations and two variables is that a solution like this meant that there actually was no solution. If we ran into a problem like this, we actually got no solutions. So we would say here that this is no solution. It's called an inconsistent, I'm pretty sure I'm spelling that wrong, system. And I'm more concerned with the fact that you know that that just means there's no solution. All right, so for the last one for the week, we have three equations, and there are three different variables being used. Now, not all three variables are being used in all three equations, but we still have a system of three equations and three variables. Once again, I want to try to eliminate one variable out of two different equations. Now, what's really nice here is that I've already got an equation that just has y and z in it. So why don't I go ahead and use the first and last equation and eliminate x in those two equations. So if I take the first and the third equation and I eliminate x. Okay, so let's add these together. And since it's already positive 1x and negative 1x, those are going to actually add up to be 0. So what we end up with is 3y minus 3z equals 0. So we'll call that equation 4. And now I've got a 2 by 2 system, right? I've got two equations with two variables. So let's go ahead and put those two equations together. So I've got equation 2, which is y minus z equals 0. And equation 4, which is 3y minus 3z equals 0. Okay, I'd like to be able to eliminate a variable here. However, I can't right off the bat. But if I were to multiply equation 2 by, let's say, negative 3, you know what, let's even just make it positive 3. Let's see what happens. So that's going to make equation 2, 3y minus 3z equals 0. And equation 4, wait a minute. Those are the same exact equation. So if I were to add these together, I get 0 equals 0. Now, that's very different than what we talked about a few minutes ago, right? I'm not getting like 4 equals 0, which is not a true statement. 0 equals 0 is true all the time. So how do I represent the solution for this? For right now, and because we're not really getting into like the nitty gritty of this, we're just kind of skimming the surface. I want us to just understand that this means that there will be an infinite number of solutions. Just like we would see in a 2 by 2 system, it's an infinite number of solutions. Now, what's interesting about this, and we aren't going to go into the, like I said, into the details here, is that what this solution actually will be is a line. And we would have a way of representing that solution with an equation. But for right now, I just want us to understand what that means when we end up with something like 0 equals 0. It tells us that there's an infinite number of solutions. We're not going to worry about how to write that. If you can just tell me that there's an infinite number of solutions, that's a really great start. Next year, you can talk more about how to write that solution in a more exact manner. All right, so for this video, for this content, I'm going to have you practice by solving these 4 systems of equations. I'm going to give you a place in Classroom. I think it'll be a Google form where you're just going to put your solutions, and then we're going to ask you to upload your work as well. So you'll have a Google form that'll ask you what's the solution to A, what's the solution to B, what's the solution to C, what's the solution to D, and then you'll finish that up, but also as part of the assignment, you'll upload your work to that assignment on Google Classroom as well. And you'll also see in that Google form, I'm going to give you kind of a challenge problem. So it'll be a bigger system, maybe 4 equations with 4 variables or 5 equations with 5 variables. It's an optional question, but I'd love to see if you can figure out how to solve that. And then that's it. That's it for the year. That's it for this week. That's it for the year. It's kind of, not the way we all expected the year to end, but I just wanted to let you know that I'm proud of you. And I miss you, and I can't wait to see you walk in the halls at Gehenna next year. Guys, have a great summer.